Irodov problem number 1.127. A small body of mass m is located on a horizontal plane at the point O. The body acquires a horizontal velocity v0. Find A, the mean power developed by the friction force during the whole time of motion if the friction coefficient is k and the mass and v0 are given. And B, the maximum instantaneous power developed by the friction force if the friction coefficient varies as k equals alpha x, where alpha is a constant and x is the distance from the point O. So this question you have to interpret it correctly. So what it says is, here is a horizontal plane and a small mass m, okay. It acquires a velocity v0. So it starts with a velocity v0 here, and then it goes, let's say, up until point A, and due to friction it stops here. So velocity here is 0, okay. So the mean power that needs to be calculated for the entire time of motion is from O to A until it stops, okay. So if I look at the mass at any point, if I draw the free body diagram, it is mg, there is a normal reaction, and then there is a frictional force, okay, and the body stops due to the frictional force, okay. Now, so the friction force we can write as Kn, the coefficient of friction times the normal reaction, and that is nothing but Kmg. Now this is the constant frictional force. So we can calculate the deceleration or the negative acceleration as force divided by mass. So that is kg, and that is constant deceleration. So if it started with velocity v0, ends with velocity 0, we can write v equals u plus at. We can use this formula, which is applicable only for constant accelerations. So this is a constant acceleration case. So final velocity is 0, initial velocity was v0, and acceleration is in the negative direction as compared to v0. So acceleration is minus kg into time. So that will give me the time it takes for the body to move from O to A and stop at A, okay. So the time t is v0 divided by kg, okay. Next we can look at work energy theorem. Now work energy theorem, if I apply that between point O and A, so the total work done by all the forces is equal to the change in kinetic energy. I keep repeating that it is work done by all the forces is equal to change in kinetic energy. So although there are this gravity force, the normal reaction force, those are present, but the work done by mg and n is 0 because they are at perpendicular to the direction of displacement. But always remember what the work energy theorem truly states. It says work done by all forces is equal to the change in kinetic energy. This will reduce to work done by the frictional force is equal to change in kinetic energy, okay, because that's the only force that has some non-zero work done, okay. So work done by friction is delta k. Now delta k, change in kinetic energy, is kinetic energy final minus kinetic energy initial. Now kinetic energy final, the body is at rest, so that's 0, and kinetic energy initial is half mass of the body times it was moving with v0 velocity, v0 square. So the total work done by friction force is half m v0 square, okay. Now, so the mean power developed by the frictional force is total work done by the frictional force divided by time. So this is minus half mv0 square divided by time is v0 by kg. So this is equals to minus, we can cancel out one v0, so mv0 kg divided by 2. Now for part B of the question, so let me just write this down as part A. Let's do part B here. So for the part B of the question, it says that K, which is the coefficient of friction, varies as alpha x, where x is the distance from O. Okay. So now the question asks to calculate the maximum instantaneous power developed by friction. So instantaneous power we can write as friction force times velocity, but velocity is in the positive direction, friction is in the negative direction, so minus Fv. Okay. And now we have the friction force as Kn. So this is alpha x for K and N is mg. Okay. So we can write this as minus mg alpha x times v. Now we have to do something about this velocity, because this velocity will be some function of x. Okay. How can we find velocity? So from here, force, if this is that, acceleration is actually, will make use of the signage now. So this is minus F by m. So acceleration is minus alpha gx. So why minus? Because this is actually negative acceleration. Okay. So for as x increases, acceleration is negative. X is positive in this direction, acceleration is in the opposite direction. So acceleration we can write it as dv dt. Okay. Or we can also write dv dt as dv dx times dx dt. What is dx dt? It is v. So this is v dv dx. Okay. And that is equal to minus alpha gx. Now we can bring this dx on the other side. So v dv is equal to minus alpha gx dx. Now let's integrate both sides. What will be the limits of integration? Initial velocity was v0. At any time t, let the velocity be v. Initial x was 0. At any time t, let the displacement be x. Okay. So if we solve this, this becomes v square by 2, limits being from v0 to v, and this side becomes minus alpha g is a constant, we can take it out, x square by 2, limits being 0 to x. Okay. Okay, now let's put the limits. So this is v square minus v0 square divided by 2, and this 2 we can cancel out, so I'm not writing that. This is minus alpha g x square minus 0, so x square. Okay. So therefore v square is v0 square minus alpha g x square. Okay. So from here I don't have too much space down below, so I will write it here. V is root over V0 square minus alpha g x square. Okay. So now we have an expression for instantaneous power. We can write this as minus mg alpha x times V is root over V0 square minus alpha g x square. Okay. Now, for maximum instantaneous power, we need to find dp dx, because x is our variable here, equals 0. So let's differentiate this with respect to x. Okay. So if we differentiate this, minus mg alpha is a constant. So let me write dp dx equals minus mg alpha is a constant, x times differentiation of this. So half V0 square minus alpha gx square minus half times minus alpha g 2x. Okay, so this is multiplication plus root over V0 square minus alpha g x square times differentiation of x, which is 1. So let's go to the bracket. Okay, so we can cancel out this 2 and this 2, and okay, minus mg alpha, denominator is V0 square minus alpha g x square square root. So this is this first term numerator is minus alpha g x square plus this times this, so V0 square minus alpha g x square. Okay, I'm running out of space, but hopefully we are almost there. So mg alpha, new denominator is V0 square minus alpha g x square, and numerator is V0 square minus 2 alpha g x square. Okay. So when dp dx is 0, then V0 square must be, this numerator must be equals to 0. So this V0 square must be equals to 2 alpha g x square. Okay. So then, if this is the condition of maximum instantaneous power, so we can write P max, we substitute this V0 square or value of x into this. So we can write minus mg alpha, x is how much? V0 divided by root 2 alpha g. Okay, and alpha g x square is V0 square by 2, so this becomes under root V0 square by 2, so this becomes V0 divided by root 2. Okay. Now the simplification is easy, I believe. So minus alpha g, so m v0 square root alpha g divided by 2. So this is our maximum instantaneous power. Okay.